Hey everyone, this is a coding tutorial about my plugin ALLHaas. More specifically about some of the considerations that I had to take in order to design the structure of the filters that are used in the plugin. Before we are jumping into the code, I want to give you a quick overview what the plugin is actually doing. So there are left filters and there are right filters, and it's all Allpass filters. Cutoff frequency, distance is the amount of filters. So as you can see, it can be a lot of filters. And feedback is how squashed they are in a tight space, or if they are more like spreading across the whole spectrum. So even a single all-pass filter can be spreading across the whole spectrum or be a little bit tighter, and that's for both of the sides. So this is basically some sort of disperser clone but with stereo features, or diopter. If you want a free alternative, diopter by Robert, links in the description, of course. And there is also a mid-side mode which cannot be displayed in EQ Curve Analyzer 2 because EQ Curve Analyzer 2 sends an impulse that just has no side signal. But if there was side content now, then there would be another phase shift visible. So here we are now in the code, and now I will mess with the code a lot in order to, get to the bottom of this whole thing. Here we are currently in the ProcessBlock method, which basically just works like this. It starts with the things that always happen at the start, where you clear all of the buffers that are not used, and then you return if num samples is 0, because that means that there is no sound currently running through the plugin. One thing about this plugin which makes this special is this plugin can only be instantiated on stereo channels, and that's pretty unusual. Usually you try to design your plugins so that they work on both mono and stereo channels, but since this plugin is about stereo widening, it just has a very simple buses layout, and that also enabled me to make some of the stuff in ProcessBlock a little bit easier. Now next up we have all of the parameters which are loading their values: cutoff, feedback, distance, num filters, and whether or not we currently are in mid-side mode. If we are in mid-side mode, then we encode to mid-side and decode back to left-right at the end, and if not, we're just jumping straight into the process. At the end there is also the mono parameter, which takes away the side signal, and the oscilloscope, which I will not talk about in this video, even though it's also really interesting. Maybe I will make another video. Let me know in the comments if you are interested in the oscilloscope. Alright, so here we are in the header file where there are already two classes for the ALLHaas implementation, and I will add another one, ALLHaas tutorial, and I will use this class to just show you some different considerations that I had during the development of this plugin. So let's go into the Allpass header file, and we see all of the different implementation of Allpass filters that I have here, and we are just starting with the first one, the Allpass transposed direct form 1. So let's just say that we have one of these filters here. Let's find out what can we do with this filter. It has exactly two variables, y1 and g. You can reset the filter, which makes sure that under modulation it cannot break out. However, it also causes discontinuities. It's still useful though, we will get to that. Then there is a copy from method, which is used for if there are multiple filters, then one filter can copy the coefficients from the other filters so that they don't have to be calculated again. Then there is update parameters, which currently just gets the frequency in hertz and the sample rate, so just one parameter basically, and the processing function with an input sample and an output sample. Alright, so let's copy the processing function from one of the other ALLHaas classes. So if we now try to implement this filter, we could, for example, do it like this, looping from 0 to num samples, and just saying, okay, the first channel of this sample index is the filtered sample. Of course, we also have to update the parameter values. Filter, update parameters, cutoff left. And now we need the sample rate. So apparently we also need a prepare method. And the sample rate as a member variable. That's all that we can do with this Allpass filter. But it's not a lot. We only have processed one channel, the left one, and we couldn't even change the feedback amount. Since we only have one channel, we can also not change the numbers of filters, especially not per channel. And that's just the thing of the Allpass transposed direct form 1. It has a very simple update parameters function, which only updates one coefficient. As you can see, the copy from method also just copies this single coefficient from another instance. And the processing is also really simple, which is nice. So if you only need an Allpass filter with a cutoff frequency, then this is perfectly fine. But of course, there are some other Allpass filter implementations here for a good reason, and I will show you them now. By the way, the code is open source, so you can go check it out yourself if you want to, link in the description. And that's also why I added some comments here. So this thing has no bandwidth. It has, I was told, numeric instability. That's why I implemented it with double instead of float, so that I don't have to deal with that, hopefully. And I didn't until now, at least. Modulation issues means that when you try to modulate it, the filter can break out. You can get some loud peaks sometimes, but it can't break out forever like most filters. So the next one that we have here is Allpass Transpose Direct Form 2, which also suffers from numeric instability and modulation issues, but it has bandwidth. You see, so there is a new update parameters function which does take the bandwidth into account, and it has also a little bit of a more complex update parameters function. Actually, some of this is kind of nonsense. We are working with double here and not with float, but yeah, I was working on this plugin really quickly, so I didn't pay perfect attention to every single step, I guess. Now that makes more sense, but yeah, it still worked, so it doesn't matter. The processing function also looks a little bit more complicated, has a few multiplies, a few adds. It's still a pretty lightweight function, but it is more than direct form 1. So here we have Allpass second order B-cut, which has quote-unquote bad performance. I should really put that in quotes because it's not that bad actually, but no bandwidth, by the way. So here we have a similar situation as in direct form 1, but no numeric instability, and I think also no modulation issues, but I'm not quite sure. I would have to test that, I guess. But you can already see there are much more coefficients going on here, so that's why it performs worse, because when you have to copy stuff around from such an instance, then it's just a little bit more to do. Also, the update parameters function is, I would say, around as complicated as this one, even though this one doesn't even have bandwidth. So it's a bit of a trade-off, and the processing also has a lot of multiplies and adds and equals. I think one equal more than this one. Equal, and here equal. Yeah, one equal more, and also this one. But yeah, when I say bad performance, it's like could be neglected, but it's worse than the other one for sure. And yeah, Allpass second order B-cut with bandwidth. As the name already suggests, it's almost the same, but this time it has bandwidth, which is nice. So also a lot of stuff to copy, also a lot of stuff to update the parameters, and also this processing function, which is numerically stable, just an IIR filter, but it performs slightly worse than the direct forms. Okay, now let's just pretend that we want to use the direct form 2 because it has a good performance, and maybe we don't care a lot about modulation, accuracy, or numeric stability, so we can use that. So now we can finally use feedback left hertz. Now we have fixed this problem already. We can use two of our parameters now. However, this is still just the left channel and it doesn't have num filters in it yet. So we still need to go on and explore more of these Allpass implementations that I made here. So this is Allpass stereo. So let's just find out what we got when we use this one. And now we see that the processing function doesn't work anymore because now it wants to know the channel index as well, which is nice because we do have two channels. Note that this plugin always has two channels. That's why I don't have to put num channels here, but just the magic number 2. So now the processing function works again and update parameters still works the same, but I hope you noticed the problem. Do you notice the problem? I give you some time to think about it. Okay, enough time. The problem is we are processing for two channels now, but we are using the parameters of just the left channel at the moment. For some reason, we cannot give the Allpass filter individual parameter values. Why is that? The reason is because I implemented this to have a really good performance, basically by saying, okay, just filter 0 updates the coefficients and filter 1 just copies from filter 0, so that filter 1 doesn't have to do anything smart but can still work with updated coefficients. So that cannot be the solution because we do want to have separate parameters for left and right when we want to make a stereo widening effect like that. So let's check out the next thing, Allpass slope. Okay, let's try to implement that. And we see the processing function again doesn't work. I know why, because Allpass slope does not have the concept of being stereo. But Allpass slope has the concept of a number of filters. So now we are back at an implementation that looks a little bit like just a single Allpass filter, but instead we have a lot of Allpass filters all on the same cutoff and bandwidth setting, and we can change the number here. And I decided to implement this because it can also be optimized very nicely, because you only have to update the coefficients of the first Allpass filter, and for the rest of the filters you can just copy the coefficients, which is nice. And in the processing function you don't have to use all of the filters all the time, but just of how many filters you are currently using as defined by the parameter, which is also nice if this works for the context of your plugin. But it doesn't work for mine, of course, because we do need both stereo and slope, and that's why I made Allpass slope stereo. So let's put Allpass slope stereo filter here and find out what this wants from us now. Now the processing function doesn't work anymore, and I know why, because this object of my Allpass filters wants to know the channel index again. So it is stereo apparently. And what about update parameters? That's still the same, frequency, Q and num filters. So we are still only using the values for the left channel. And why is that? Why would that be useful? Let's check it out. So update parameters now works like this. I'm updating the first Allpass instance. And what kind of Allpass is this? Let's find out. So we have an array of stereo Allpasses with the amount of the maximum number of Allpasses, which in this plugin is 128. So that means update parameters goes into the first stereo instance of an Allpass filter, updates the first of that, and then copies to the second. And then I'm looping through all of the other filters and do the same, but this time only copy. And copying for the stereo instance means that you can copy into both filters from some stereo Allpass into another. So this is also a greatly performing thing, but it doesn't let us use cutoff right, feedback right, and num filters right, because it assumes that the parameters do the same thing for both channels. So this would be nice if you just wanted to make a clone of disperser or diopter, then this would be the perfect class to implement, as you can see. But I wrote another one, the Allpass stereo slope instead of slope stereo. And if we put that here, then it works like this. Now we have a function that wants much more information from us. And the processing function still works the same, I guess. So as you can see, now I could finally use all of my input parameters. So this works. Let's check out what it does. So this is an array with two instances, so stereo, of Allpass slope. And as you remember, Allpass slope is just a bunch of Allpass filters in series with the same parameter values. So this is the layout that we have to use for these kind of things. And this actually has the worst performing update parameters method of all of the classes, because it has to take both the 0th and the first Allpass filter and update the parameter coefficients, and cannot just copy stuff over, because it has to use unique values for each of them. Okay, now that we got this out of the way, let's just remove the ALLHaas tutorial struct again and look at the ALLHaas struct, because that's basically the same thing but just written slightly differently. So here we have what I did. I also wrote a prepare method, a processing method, update parameters and process filters, and also gave the class a bunch of values for the parameters. I made sure that the default values of the parameters don't make a lot of sense, so that they are updated immediately on the first time ProcessBlock is called. And also when the sample rate changes, you want to let at least one of the values be nonsensical, so that it triggers the update again. Forgot to do that last time, but I didn't end up using this class anyway, so it's cool. And in the processing function, I separated the process into two things: update parameters and process filters. And update parameters works like this: if all of the parameters are still the same, return. And if not, then they are all updated. I'm also calculating the cutoff frequency in hertz from the cutoff frequency, which is currently in pitch, and then update the parameters with that. And the process also works really simply, you know, looping through the channels, looping through the samples, and let's go. You already seen that. But are we done here yet? I mean, the answer is obviously no, because otherwise I wouldn't say it like that, but Let's just, for now, try what would happen if I used this class instead of the one that I actually use. So all changes I have to make for that is making the prepare function a little bit shorter, and I think everything else is still the same. So let's build this now. Alright, back in Bitwig, we can now check out what the plugin is doing, and we see it still does the correct thing, still does the same thing as before. Everything alright, but now let's actually try to use it. I have to make a different patch, something that sounds a little bit more obvious when an Allpass filter is applied, something rhythmic. Okay, so first of all, you heard some scratchy noises when the distance parameters are moved. That's not too much of a problem. A lot of plugins that are like that. Just accept that if you change the amount of filters, then the user should expect a discontinuity. I would also say that's okay. That's not a big deal. But let's just try adding randomized modulator to the cutoff frequency left. Oof. Holy shit, that was loud. And the reason for that is because these filters do really not like steppy modulation. Yeah, and that's all that I wanted to show you for now. And the solution for that is typically to implement crossfades, which is why I made the ALLHaas XFade struct. So first of all, before forgetting it, I wanna put this back to ALLHaas XFade so that I don't have to listen to these ugly artifacts anymore. Perfect. Now, we already saw all of the Allpass implementations. So you can imagine that the ALLHaas XFade class doesn't use any new type of Allpass filter, but it just adds the crossfade. So here we have the ALLHaas XFade class. So let's just look at it from the header, so that we can get a little bit of an overview. There is a new static constant export in num tracks and a fade length in milliseconds, and you can see, okay, apparently there are two tracks in parallel, and when they kind of change which one is the main track, then the crossfade takes 40 milliseconds. Yeah, that's just a value that you have to tweak. If you take a value that is too short, then the transitions sound very obvious. If you take a value that is too long, then the plugin doesn't feel responsive. So you always have to kind of balance that, and it can be a very different value depending on the process that you have to crossfade. So don't just take my word that 40 is a good value. So here's the constructor. The prepare method now has the block size in it. The processing function still looks the same, and there is still update parameters and process filters. And this is almost the same, except now there is an XFadeMixer as well. And now the Allpass stereo slope is not just a single object, but there is actually an array of that also has num tracks, just like the XFadeMixer. So you have to synchronize the amount of filters with the amount of tracks in your project. Now here we are in the CPP file, and now here in prepare you can already see why I added the block size, because it has to be given to the mixer. The reason for that is the mixer prepares some buffers that have to have the block size, because otherwise you could not fill them with parallel audio processing stuff. Now update parameter still looks almost the same. As you can see, there is just a little bit of a difference, which is before even asking if the parameters have changed, we ask if the mixer is currently capable of fading, because the mixer is always switching between the first and the second track, and if it's still in the process of going to the next track, then you cannot update the parameters, which is why you return. So even if there are new parameter values, they just have to wait until the mixer is done fading, and then we are doing the checks. And then at the end, since we know that we now need a new crossfade, we tell the mixer to init a new crossfade, and then we update the parameters, but only the ones of the filter that now is the main filter. So you can imagine it a little bit like this. There was a track and it wasn't being used, but now the mixer has just freshly told this track to be used again, so it currently has a gain value of 0. So now when you update the filters with the parameters, that might usually suck when it comes to modulation, but I just put a reset right after, because the volume is at 0 anyway. And what does reset do? It calls the two instances of the slope Allpass filter to reset. And what does that mean? It means that for each of these stereo Allpass filters, all of the slopes are being reset. And what does that mean? It means that Z1 and Z2 are 0. So this is a very good performing operation, which is nice. And the processing function also got a little bit more complicated, and I will get into the implementation of my mixer very soon. I made a video about that before, but I will just take the liberty to explain it again in this video because I feel like it's actually one of the things that I did very well and I should get it out of there a little bit more. So in this case it works like this. I just decided that the first channel of the mixer samples, which is the internal buffer, is the sum of all samples. And then in these brackets here, in this scope, I just get the first track out of there and I ask, is the track currently enabled, which means is it currently in use or is it gain 0? If it's currently in use, then I synthesize the next gain values, which is a curve that moves it from 0 to 1 or from 1 to 0 at any point, or just stays at 1, depending on what currently the job of this thing is. Now for num samples, and it's being synthesized into the third channel of some samples because I designed my mixer to always use the first 2 channels for audio and the third channel for the gain values. Now I get the instance of the filter out of there and just do the same thing as I did before, almost at least. You see, I'm using the buffer from the some samples now because I'm taking the samples from the sample buffer, but I'm actually processing them into the track of some samples. At the end, I copy some samples into some samples. Oh yeah, I remember why this makes sense. Because in the copy method of my mixer, and this could still be optimized, I am actually using the gain values. I should write a new method that doesn't have the copying in the process but just the gaining. Well, anyway, if the track however was not enabled, then I'm just clearing some samples at that point, because that's something that you often do when you have to parallel process. Either your first layer does have some information in it right from the start, or it is just cleared, so that every other process that comes now can be made with addition instead of copying. And that's why this is like a separate step from whatever comes next with this for loop. So this for loop basically does the same thing, gets the track, if enabled, does stuff, but the difference is instead of copying, it adds to some samples, right? So at the end, we just need to make sure that some samples is being copied back into samples, and then you have it in the samples buffer and it works. Maybe this could still be made a little bit better in terms of workflow. I don't know, if you have any cool suggestions, let me know. But for now, I will just show you how it works at the moment. So if you go into my open source project, into the XFade header, you can skip the whole struct XFade because it's like an older thing. But XFadeMixer is the thing that you need to pay attention to, and it works like this. It basically, just to get an overview for now, there is a struct called track, and that's very important, and the whole thing has an audio buffer and an array of tracks and an index, and the index always describes what's currently the main thing you are moving to. So this is like a ring buffer, it keeps on moving in circles whenever you hit init, because init means initialize a crossfade. In prepare, we are preparing the buffer with 3 times num tracks and block size. We are setting the increment value for all of the tracks as defined by the length in milliseconds, and give it a default value with a gain. As I said before, when you hit init, it just moves the index 1 further, and with the modulo moves it back to 0 if needed. Then it disables all of the tracks and only enables the one that needs to be enabled. So here's a little method for returning a track. Here is what is important about a track. You've seen me asking if the track is enabled, which just means that both the gain and the destination gain is some value that is not 0. So gain is the current gain of the track and destination gain is where it wants to go. So if you are currently in the process of enabling it, then it wants to go to 1, and else it wants to go to 0. Is fading also works almost the same. Synthesizing the gain values. If you're currently not fading, it means that you're just filling the gain buffer with the current gain value. But if it is fading, then you have a little bit more to do. This is just ramping values. And if you've used the smooth template to true, then there is a little bit of an extra feature that remaps this to be a smooth curve. As you can see, between 0 and -1, this is a smoother curve than just this. This is what the smoothing thing does. I also use that in this plugin. It often makes the transitions more natural. Yeah, and that's basically all you need to know about each track and the XFadeMixer. Let's build this again. As you can hear, now there are no nasty gain spikes anymore, because as you've seen before, we are resetting the filter every time the parameter values change, and it's just softly transforming from one filter output to the other. That makes it slightly harder to hear the difference in sound immediately, but if you just tweak the crossover time as good as you can, it works pretty fine. There is one thing that I didn't mention. You could also try to work this out with parameter smoothing, and I bet a lot of people have watched this video and screamed at their screen because they were thinking like, why is he not talking about parameter smoothing? But if you know me, then you know that I usually talk about parameter smoothing and that I took a lot of care writing my own parameter smoothing class, but I avoided parameter smoothing on purpose here, because it would mean, and it's often the case in the context of filters, that I have to update everything per sample, which would be quite a lot with all of these Allpass filters, quite a dramatic CPU hit. Yeah, and I didn't want to do that, even considering that it might have reduced the gain spikes a little, but it wouldn't even have made it impossible to get some nasty gain spikes, and the difference in tone wouldn't even matter because this plugin is not actually meant to be modulated a lot. That would be more of an abuse. So you would have a constant CPU hit just for the rare case that someone feels like you have to modulate this like crazy. Yeah, in situations like that, it is usually better to just implement a crossfade. Sometimes people even like the sound of crossfaded DSP processors more than the sound of parameter smoothed ones. I typically like parameter smoothing more as a sound because it can have its own little quirks. For example, in the context of delays where it introduces nice pitch drifts and stuff. Can also happen with filters, especially here Allpass filters and stuff. But yeah, the goal was really not to let people go crazy with modulation. It was to have a more or less optimized and CPU friendly version of disperser on each channel. And that's how you can do that. I hope this video was interesting for some of you who consider writing their own filter plugins, because you really have to take care to think about the way you want to structure your filters, because otherwise you end up having to rewrite half of the plugin just to get the functionality done that you have in mind. And maybe that's even cool because it's kind of a fun process. But if you ever feel kind of disappointed by your implementation because you are kind of stuck with the wrong structure, then you can keep this video in mind and feel encouraged to just try again and now write it all again, but with a better structure. Alright, enough of this video.